lot here, at least one person. Oh yeah, she, Ray, and Austin. Austin will probably watch this. You can download it and watch it on the plane. So there is homework. I just shoved it. I was like, well, we'll just have it all due on Monday. So I know it's Monday, but whatever. So there's a whole bunch of homework here. We'll do the best we can, try to get it all in. So it's all systems. So we better get to work on the systems. So first things first, just a quick note about direction fields. So what is a direction field? The direction field is just a representation of a system of differential equations. Let's see. I wish I knew what that direction field was for. Well, let's make a new direction field. So we have dx over dt is equal to negative x plus y, and dy over dt is equal to x minus y. Good enough. No, let's make that a plus, just for fun. Okay, so direction field, similar to a slope field. You know about slope fields, don't you? So direction field, very similar to a slope field. What you're going to do is you're going to make a little mark on your graph for each point pointing in the direction of the solution. So for example, right here, when x equals 1 and y equals 1, x equals 1, y equals 1, what is the direction you're going? You have to bear in mind that we have two different slopes here, and so you have to think in terms of, how fast you're moving one direction versus the other direction. So if x equals 1, y equals 1, notice that dx over dt ends up equaling 0, and dy over dt ends up equaling 2. And so what I'm going to do is I'm going to put an arrow. It's not going to be 2 units long. I'm going to shrink it down, but it's going to point upward because your slope is 0 in the x direction, so no motion this way, 2 units in this direction. So we could do this for every point on this grid. It gets a little laborious to write things like that. And so instead, what I'm going to do is I'm just going to write it like a vector. Like back in calculus when we had vectors. So that point is the point. So this is the point 1, 0. So when x equals 1, y equals 0, the slope in the x direction is negative 1. The slope in the y direction is 1. So I would draw that as a little arrow going that way. Now these aren't really to scale. They should be to scale, but they aren't. But so this 2 units long, this one would be what, radical 2 units long? I don't know, 1 unit back, 1 unit up. But this will at least give us a feel for what's happening with this particular solutions, and hopefully give us a clue as to what we mean when we do our solutions. So we'll get to the solutions. I know we did a few last week, but we'll do some more this week. So let's put a few more dots on here. So let's see, let's do the main dots. Here we go, just those points. So at the point 1, negative 1, find your direction. So take a minute and do that. We're going to go around the circle. The point in the middle is special because that's a equilibrium, in the sense that if you're sitting there, you're not going anywhere because the slope in the x direction is 0, the slope in the y direction is 0. So I'm going to just put a dot there. In fact, every system that we look at from here until the end of class is going to have an equilibrium there. We don't have time to get into other situations, so you just have to trust me that if you move this, like you could translate this to another location and have an equilibrium elsewhere. But for now, equilibria are going to be at the origin. Okay, so we need to find all of these, and I need to pick a random person. I know you can all do. Oh, that's not what we want. Oh yeah, I could just pull this over. Just a sec. There we go. Yeah, let me do attendance. Mark these people absent. Should you think it's okay for me to mark Austin unexcused? Let's see. Differential. Take attendance. Let's see. Austin. Okay, I'll excuse him for today, but not Friday. Luke, I think Luke is excused. I'm going to excuse him. Isn't there someone else? Oh, Asal? No one else? No one sits up there with you guys? You're just the only two? All right. That's it. Let's do it. Submit. Okay, let's go. Oh, what point was doing this? All right, Cooper C. Cooper C. With this 1, -1, that point, what direction are we're moving? -2, 0. So that means straight weight, -2, 0. That's straight backwards, right? Okay, so it'd be something like this. All right, let's be systematic about this. We'll go across and down. So, whoa, what happened there? So here we'll start with this point, -1, 1, and then we're going to do 0, 1, and then back here, -1, 0, and then this point, -1, -1, and then 0, -1. Okay, so let's go across. Start with -1, 1. So who gets to do that one? It's pretty straightforward, though. Rachel P., what do you get when you plug -1, 1 into this? 1, 1. So that's up and to the right. Excellent. There we go. Wait a minute. 1, 1. Oh, 0, 1. Okay, yeah. I'll do that one then. Yeah, we'll back up and we'll do this one again. Yeah, I was going to say it doesn't seem right, but I trust you. Okay, now we do -1, 1. Very nice. So, oh, you're not here, but Mariah is. What about that -1, 1? Let's get that one. This one right here, -1, 1. That one right there. Yeah, sorry. Yeah, Rachel was looking at the wrong one, but we got it. Wait. 2, 0, over 2, up 0. So it's going to be something like this. Interesting. Starting to see a pattern, maybe? We're going to find out. Okay, Rachel J. I don't know, pick one. Okay, so up 1, back 1, wait. 1, -1, over 1, down 1. Okay, like this. Okay, very good. Yeah, it's a little confusing. Almost there. You're not here, but Adric is. Adric, what about pick another one to do? All right, where do you go? Where does that end up? -1. All right, so it goes back and down. Interesting. Wow, this is kind of weird. And then one more, Joshua. You get the last one, that bottom left. 0 and -2, over 0, down 2. So we're going down like this. Wow, it's hard to make heads or tails of this, but it looks to me, and we can, we will be able to tell better if we had a computer do this, but it looks to, and actually we can do better if we actually solve this. It looks to me like the solutions are doing two separate things. Either they're going like this, sort of down that way. And I know I kind of fudged that one a little bit or messed it up. Or the other direction, they seem to be coming and going up like this, or maybe like this. So you see how, so all of the solution, like this is an equilibrium, and solutions are kind of flowing inward, and then they split off. Some of them go up here, some of them go down there. Things come in this direction, and similar deal. They all kind of split off and go different directions. Okay, well, this is really hard to tell with this, whereas if I drew a much better, this is a better rendition of slope field. So this a computer did for me, and you can actually see all of these arrows. What's happening, sort of, at least a general idea, is that you have solutions going out that way, kind of curving up and around and going parallel in that direction. And so here you have an equilibrium here. So this is our equilibrium at the 0, 0 point. But then all the other solutions, they either, well, here, this thing goes this way. This one's going to go, looks like straight line down that way. And then you have other solutions that kind of curve their way upward towards that direction or downward in this direction. So you have various solutions that go in those directions. So that's what we want to know, is we want to know in general what's going to happen to our solution in the future. Like which of these paths are we going to follow based on where we start. So we've already talked about eigenvalues, eigenvectors, so we don't want to bore you with that. But what I do want to bore you with is this. So let's see, go back to, do I want to do this one? That one is so boring, but it might be helpful. No, it won't be helpful yet. That one's not helpful yet. Let's do this one. Let's go to this one and see. So here's what I want to do is I want to connect this to this. So the two pictures, try to understand the relationship. So remind you how to get eigenvalues, eigenvectors. So what we're going to do is we're going to start off by doing the determinant of the matrix, but you subtract lambda because we like Greek letters in mathematics, don't we? 3 minus lambda. So you put lambda along the diagonal. So you just take the matrix and just put the lambda on the diagonal. And the reason why we're doing this is we're looking for these straight line solutions that, well, we'll relate it to the actual straight lines in the slope field in just a minute, or the direction field. But find this determinant. So go ahead and see if you can do this. We're going to solve this equation. I want to know, where is that equal to 0? I don't remember, did we use an r instead of a lambda last time? The lambda is what all the linear algebraists like to use, so might as well use a lambda. Wow, it keeps picking people who aren't here. So take a minute, do the determinant first, and then I'll find a volunteer to do the determinant for me. All right, Matthew, do you want to talk me through this determinant? Like, what do I do? Beautiful. So you're just doing the diagonals. So down diagonal minus up diagonal. Perfect. So a little bit of algebra. This isn't too hard, I hope. So we got lambda squared minus 5 lambda plus 6 minus 2. So lambda squared minus 5 lambda plus 4. All right. Well, hopefully I can factor this. I'll bet you can. Take a sec, see if you can figure out what the factors are. Well, Claire, do you know what the factors are for this thing? Ah, yes. So lambda minus 4, lambda minus 1. So that means lambda equals 4, lambda equals 1. So those are the eigenvalues. And that's going to be the first piece that we're going to use to come up with our solution. Second piece are the eigenvectors. So we need to get those squared away. And I know I'm doing this pretty quickly, but I think we went over it before. So just to remind you how you get your eigenvectors, you take each of these and shove them in right there into where the lambda is. And then we're going to solve, we're actually going to solve the equation. So let's see, 2 minus lambda. I got to remember this thing. So here it is. So we have 2 minus lambda and 3 minus lambda, and there was like a -2 and a -1, I think. Let me see. Yeah, that's right. And then it's 4 and 1. Okay. So lambda equals 4. We're going to do that one first. So we have 2 minus 4, which is -2. And then 3 minus 4 is -1. And this is going to equal 0, 0. And so if you're not familiar with linear algebra, the easy thing to do here is just to think in terms of, that these are coefficients for an equation. And the equation that you're going to write down is just coefficient times the first part of the vector plus the coefficient times the second one is equal to 0. And then the second equation is -1 v1 and -1 v2 is 0. Now, if you've done this correctly, those are the same equation. In fact, V1 is negative V2, or negative V1 is V2, however you want to do it. And so now you get to choose whatever you want for V1, and the other thing is going to, the V2 is going to be determined by whatever you pick for V1. So I'll let you pick, and Max wants to pick the number. What would you like for V1? 1, I love it. 1 for V1. And so if 1 is V1, V2 has to equal -1. So my first vector that corresponds with the eigenvalue, sorry, it looks a little scrunched up here, 4 is going to be 1, -1. And I'll show you where this goes in just a sec. But for now, let's get our second eigenvector. There we go. So let me set this up. So now I'm going to use lambda. Whoa, that's a V. Lambda is equal to 1 was the other eigenvalue. So we have 2 minus 1, and then -1, and 3 minus 1, which is 2. There we go. V1, V2 is 0, 0. So let me set this up. V1 minus 2, V2. And of course, this should be exactly the same equation if you've done your job right. But however it shakes out, we're going to solve this. Those are the same equations. Specifically, V1 is equal to 2V2. So let's pick numbers for V1 and V2. Mariah, do you have a favorite number you want to use for one of these? 2 for V1? All right, 2 for V1, which means V2 is equal to 1. So, or you could have picked 1 for V2, and then that would have forced you into 2 for V1. However it works is fine. So that gives us this eigenvector, and that's the vector 2, 1. Now here's the cool thing about this, is once you have that, so we have the 2 eigenvectors, well, I guess we can put the solution down first. So let's write down the solution, and then I'll show you how this relates to the whole direction field, because it's really cool, the direction field. But here's the solution, is I will write it like this. You do x is equal to vector, well, I guess we could have a C1, some constant times the vector, where's the vector? 1, -1, 1, -1, times e to the 4t, C2, and then this is going to be the other one, which is 2, 1. Was it 2, 1 or 1, 2? 2, 1. Yeah, that's good. And that's e to the t. So if it bothers you that you have a, it looks weird like that, you can either combine those into a single vector, which I'll do right here. So C1 e to the 4t plus 2C2 e to the t. And this is negative C1 e to the 4t plus C2 e to the t. So that's one way to do it. Or you could do this, little x, C1 e to the 4t plus 2C2 e to the t, and little y, negative C1 e to the 4t plus C2 e to the t. So however you cut it, there's 3 different ways to write the solution. But now the cool thing about this is the vectors are the straight line solutions. Those are the straight line solutions. I kind of was hinting at that back here, that you had these solutions that were straight lines, and it might not be obvious to you that there are some other solutions, well, somewhere in there. Maybe I missed. There we go. That's better. Anyway, so those are actually straight line solutions back here, whereas the other one I drew another one somewhere. I don't know where it went. Oh, there it is. So here you can kind of see that there's a straight line solution, one going in, one going out. There we go. So let's draw the straight line solutions for this one. So let's see, the straight line solutions will go 1, -1. So let me draw that. Over 1, down 1. So draw a set of axes. On that axis, over 1, down 1 is this. And go both directions. And the reason I go both directions is, think about what an eigenvector is. it could be, you could have picked anything for the first number here. You could have picked like the number 7 or the number -2. So whatever you picked, it's going to be a point on this line. And then I'll put the other straight line solution over 2 up 1. So that's about this. So over 2 up 1, and then go backwards. There we go. Sorry, that didn't quite link up there, but close enough. Now for the cool part, or I guess it's all cool. Notice these things. One of them is 4t, the other one is t. Both of those are positive, which means if you're on those solutions, you're actually going to be going outward, getting bigger. So imagine that if you're on one of these lines and t gets bigger, you'll keep getting bigger. You'll keep going on that line. So you'll keep going. Same thing goes with this one. If you're on this solution and you increase your value of t, so that would be this one. So let's say that C2, if C2 equals 1 and C1 equals 0, you're on this line. And as t gets bigger, you go out. Now, the last bit to this is that when t is big, this is going to be bigger than that. And so as t gets bigger, everything in between these two starts out looking like the smaller one and ends up looking like the bigger one. So we start off looking like the smaller one, which is e to the t, but eventually, as time goes on, we're going to end up pointing in the same direction as the bigger one, the 4t, because the 4t is going to dominate. So you end up with something like this or like this. So all of the solutions end up doing that. So you have these two pitchforks that kind of every solution. So no matter where you are starting out, you can predict the future based on what things look like. So this one actually looks somewhat like this. It's a very similar graph to the one that we had there. So our job now, let's see, just make sure I get the blah, blah, blah. You don't care about that. Our job is going to be trying to sort out like what the solution looks like based on the matrix. So here's a new matrix. Let's see if we can figure out what this looks like. And so you're going to have to come up with eigenvalues and eigenvectors. And once you have the eigenvalues and eigenvectors, you can have a general solution, and you can have a nice slope field and a nice sort of straight line solutions and so on. Okay, good. Yeah, so take a minute, work this one out. I'll set it up. Well, hopefully you won't get stuck on the algebra. I know algebra is hard. But I think this is what we end up with. Is that right for the quadratic? So Andrew, were you able to factor this thing? Nice, nice. Product has to equal -4, sum has to equal -3. Perfect. So we've got lambda equals 4 and lambda equals -1. Excellent. Okay, next. You're going to find your eigenvectors. So here you go. I'll just get it set up for you. Yeah. All right, Tyler, do you have an eigenvector for the lambda equals 4? Wait, what was that again? V1 is 2v2, you said? Or so let's see, V2 is negative 2v1. Is that right? Yeah, that's it. Okay, maybe you weren't doing the second one, were you? Oh, you were doing the second one. Oh, sorry. Yeah, that one's a lambda. Here, I better label these. This one's lambda equals 1. All right, very good. So yeah, so I'll put that down there just a minute. So you said, whoops, that V2 is equal to 3V1 down here. Very good. Oh no, come back. Where are you? There you are. Okay, so I need an eigenvector for each one of these. So the top one, I think I got, do I have these right now? I've got this one, you end up with V2 is equal to negative 2V1. Any complaints about that? I could write it down if need be. No one's going bonkers. Okay, and then this one, that one's what you had, Tyler, right? Okay, good. So that one's great. So now we just have to pick numbers. So let's pick a few numbers here. Wow, all these people who aren't here, sad. Okay, but Zechariah's here. Zechariah, what would you like for this first one? V2 equals 1. Can I convince you to make V1 equal 1 instead of V2? Okay. Well, it does. It doesn't. You're right. It doesn't matter. But if you make V2 equal to 1, then V1 would have to equal negative 1/2. And that's just too much for my brain to handle right now. So V1 equals 1 will make it a lot happier for me at least. And then what about the second one? Clara, what would you like for this one? For which one? 1 and 3. Okay, yeah. 1 and 3 is good. And honestly, you could have chosen 2 and 6. I just try to avoid the fractions. That's the only thing. But yeah, this works. So let's set this up. In fact, let me show you what this looks like. First of all, over 1 and up 3, you know what that looks like. It's a straight line going up this way, kind of at a diagonal. Over 1 and down 2 goes diagonally down like this. I've actually got a picture of this. Here's the slope field. There's what it looks like without the straight line solutions. And then here it is with the straight line solutions. So here's that 1 over 1 and up 3, and then over 1 and down 2. You can actually see that. Now check it out. Look at where those arrows are pointing. So it's superimposed on the slope field. The one that's over 1 and down 2 corresponds with lambda equals 4 because it will be attached to e to the 4t, which means you're getting bigger. You're getting bigger, so you're going to go away from the center. And check it out. When you're close to this line, all of the arrows are pointing away. Same thing with this one, pointing away. With the other solution, this will be attached to lambda equals -1, so e to the negative t, which means you're going to get smaller. As t gets bigger, that gets smaller. So what's going to happen to solutions there? Well, they're going to go towards the middle. Now, just as with the other one that we did, where's the pitchfork? It was back here somewhere. Just a minute. It was way back here. There it is? Yeah, there it is. So just like this, solutions, when t is little, they will tend to point in the direction of the smaller eigenvalue. And then when t is big, they will point in the direction of the bigger eigenvalue. Same thing is true over here with this picture. When t is little, that is like a -10, little being a big negative number, your solutions will all be parallel to this line. So, and then as t increases, they all start to tend towards the other line. Same thing down here. When t is little, so solutions start out down here, and then they end up pointing in the same direction as that. So you have some solutions that go like that. You have some solutions that go like this. Sorry, that was a terrible but that's the best I'm going to do. So interesting, all the solutions, but you have these nice straight lines. How much time do we have? 2:44. We got plenty of time, so we can deal with some special cases. So this isn't the only thing that can happen. There are some special cases. Let's deal with them. So one thing that could happen is you could have a repeated eigenvalue. Second thing that could happen is you could have a zero eigenvalue. So what in the world, how do these relate to here? So let's take a look at this one. Wow, I guess that, yeah, there's too many words there. Let me zoom way in. There, that's better. So let's find the eigenvalues and eigenvectors of that thing. And I'm just going to copy this so that I don't have to look at all of that. Let's see. Now let me freeze this and switch over to Notability. Give me a sec. Paste it in there. Okay. Unfreeze. Much better. Okay, let's see how this works out. We're going to do this relatively quickly because I think you're not going to have too much trouble with this. We're doing the determinant of this thing. And oh, don't let me go too fast, you nonlinear algebraists. So any nonlinear algebraists who want me to can tell me stop, and I will immediately stop. So, but if I go too quickly, but I think that it's pretty straightforward. We're not dealing with anything too technical with the linear algebra. So let's see. This is going to be plus. It's all negative, isn't it? Okay, so lambda squared plus 6 lambda plus 8. Oh, yeah, that's right. Plus 1. So it's pretty straightforward. You're going to get repeated eigenvalue. Lambda equals 3, lambda equals 3. Which is disappointing because if I want to assemble a general solution to this, I'm going to need two pieces to my solution. But not to worry, we've dealt with this sort of thing before. You remember with the whenever you have a repeated root with a second order differential equation, same thing happens here. And actually the solution is going to be very similar, or the way that we deal with the solution is very similar. So let's go ahead and get our first eigenvalue, or eigenvector. So the first eigenvector, what we're going to do is we're going to do this. Let's see, so -2 minus 3, -1, -4 minus 3. Is that right? It doesn't seem right. It's a plus 3, of course. Minus. Oh, yeah, of course, because lambda is -3. Sorry, that's so dumb. Okay, that's better. Okay. That's better. Oh, and this is going to be V1, V2. Cram it in there. Here, I'm on Notability. I can move things around. There we go. So what's this going to be? It's going to be V1 plus V2 is 0. Negative V1 minus V2 equals 0. Well, that's not very exciting. It just means that V1 is negative V2. So you can pick your V1, you can pick your V2. I'll pick a volunteer. So Madison, do you have your favorite value for V1 or V2? Oh, I love it. 5 and -5. So is 5 on top? Yeah, we'll do that. 5 and -5. That works. Okay, so what does this mean? One eigenvalue for this particular system. Well, let's draw what it means, and then we're gonna have to actually come up with a solution to this, though. So here's what this means. It means that, here we go, here's this, 5 -5 over 5 down 5. So we're dealing with these as our straight line solutions. Not only that, but since this is, what is this, negative? Yeah, lambda is -3, -3. So these both go that direction, towards the center. So if I were to sketch this solution, that's what it would look like. So here's the 5, -5, and we're just moving towards the center because lambda is, you have a negative number for lambda. So what about the rest of this? The rest of this thing, well, you don't have two eigenvalues to be able to sketch the rest of your solution, but the interesting thing about this is that things will spiral towards the middle, sort of. They'll kind of spiral. And so here's how this will shake out is we first of all need to find a point that's not on here to figure out which direction we're spiraling, because you could go either clockwise or counterclockwise. And so which way does it go? Well, pick a point, maybe the point 0, 1, just for the sake of argument, for 0, 1, and we're going to put a little slope line on here. Where is my original? There it is. So for 0, 1, -2, let's see. Let's do this. So if I let y equal 0, 1, then dy over dt is going to be -2, 1, -1, -4 times 0, 1. And so what's that going to be? 2, 1, that's going to be 1, -4. So over 1, down 4. Over 1, down 4. Okay, let's go put that. Over 1, down 4, which is roughly this direct. That's not at all what it is. It's roughly, undo, this direction. Over 1, down 4. There we go. Wow, this is going to be confusing, I can tell already. Yeah, because here's the thing is that means that everything is moving this direction, but I'm going to curve around. Yeah, this is not the greatest example, but I'm going to do it anyway. So here's the way I'm going to draw these solutions is they're going to come in parallel to my, so parallel to the arrow there, there, and then they curve their way down, and they get pretty tight here, and eventually curve their way in. So it kind of spirals around. So you start out parallel to this line, and you end parallel with this line. So you kind of come in, and then it gets really tight there. Might be better to move a little bit further away. Here's another one. I'm going to fudge this a little bit to make it look more obvious. So that's what's happening up there. On the bottom, it turns out that solutions are the complete opposite. So things, you're always spiraling towards the middle, sort of. I say spiral, but you're really not spiraling. You're just kind of moving in and then twisting around, doing a 180. But that's what all of the solutions, they'll all kind of look like that, moving towards the middle. That still doesn't answer the question, though, how do we get a general solution out of this thing? And the way you get a general solution out of this thing is you use a technique that allows us to find a second eigenvector that is associated with this eigenvalue. The way you do this is we're going to basically set this. So take this thing. So I need my second eigenvector. So you take, copy just a sec, copy this, stick it over here maybe. There we go. Oh, this is a mess. Let me put it down here. So here's how this works. This is the first eigenvalue vector. And then the second one paste that in there. Here we go. Yeah, sorry, it's kind of a mess. Okay, so I need to write this down. So we got this for our first eigenvector. It was 5, -5. Okay, let me go back to PowerPoint so I can get this to be a nice equation. Here we are. Where is it? Just going to find my equation. 0. Here we go. Repeated. There it is. So here's the way you do this, is to find the second eigenvector. You're going to solve, that's not right, just a minute. I feel like these have to be switched. A minus lambda I, yeah, I need to switch these two. Those need to be, do they need to be switched? No, I think it's okay. Hopefully it's okay. We're going to find out in just a second. So basically you use the original eigenvalue or eigenvector to come up with the second eigenvector. So I'll take this 5, -5, and stick it in there where the zeros are. So let's get rid of the zeros. And in their place, we're going to put 5, -5. And then we'll solve this. Let's see what we get. So notice that we're going to get a sort of similar situation. So you solve for the first eigenvector, and then you just shove that eigenvector in and solve for a second eigenvector. So let's see, this is going to be 1, 1, -1, -1, v1, v2, and that should equal 5, -5. So whoever it was who chose the 5 and the -5, well done, because that gives us a fun algebraic equation to solve here. So v1 plus v2 is equal to 5. -v1 minus v2 also equals -5. Notice that those are the same equation. You'll always have this when you're playing the eigenvector game. You'll always end up with two equations that are the same. So now here again, you get to pick. So v1 is equal to 5 minus v2. So you pick a value for v2, and I get to pick, well, I'll compute the value for v1 based on whatever you pick. So Haven, you get to pick. What would you like v2 to be? Okay, v2 is 3. That means v1 is 2 because of this. Very nice. Okay, so now let's see if we can piece this all together. If I've got this right, my general solution is going to be, I'm going to have to look this up because I don't trust that PowerPoint. It doesn't look quite right. I do know that this is the right procedure, but here is my general solution. I'm going to have that eigenvector, 5 or 3, 2, plus t, okay, so that's C1, C2. Yeah, it just feels wrong. Just a minute. Go back here. PowerPoint. Why is that not right? Yes, I got 0 there. Yeah, I'm going to have to double check this because that doesn't feel right. Okay. I think it's coming back to me now. Sorry. Just realized doing it wrong. Start fresh. Okay, so here's how this is going to shake out. You have a constant times the first eigenvector. The first eigenvector was 5, -5, times e to the -3t. Okay, so there's my first piece of my solution. Okay, now it's coming back. C2, I have to multiply this. This is going to be a little bit more complicated. Times the second eigenvector plus t times the first eigenvector. Times e to the -3t. There, that feels right. I'm going to have to double check this though once I get my book. I'm pretty sure that that's the way that this shakes out. It's something crazy like this. The only thing I'm worried about is whether I have those two switched. I'm pretty sure this is the right way, especially since it was in the PowerPoint this way. So notice that the way that you resolve the issue with the double eigenvalue is the same way that we did back in second order differential equation land. You throw in an extra t. So the extra t goes here. And I know this is extra stuff here, but that's sort of a corrective for the t there. So I'm going to double check that though. So don't worry, the homework isn't due till Monday. So this is for me, my homework. Okay, we have 2 more things to deal with today. Well, let's do just one of them. Let's just do one of them. So one of them is complex. Well, complex is the final frontier. Let's do pure imaginary. Pure imaginary eigenvalues. So let's see what happens when we have this. Let's see. So you have y dy over dt is equal to 0 to -2, 0. I'm picking something that's relatively easy. There are other matrices that aren't quite this simple that have pure imaginary. Maybe I have one. Let me see if I have one in my PowerPoint. But I know for sure that this one has pure imaginary eigenvalues. So give me see if you can come up with the eigenvalues. I kind of hinted at it right there. Just see if I have anything good. I don't have anything good there. We'll just stick with this one. This is fine. So we'll do this one, and then we'll do the final frontier on Friday, which is the complex values. This is actually pretty easy. Okay, so if you're confused, there's what you're going to do is subtract lambda from the diagonal. So take a minute and do that determinant, and then I'll pick someone at random to show me your thing. All right, Matthew, what do you got for your equation? So lambda squared plus 4. All right, very nice. Lambda squared plus 4 equals 0. Now you can solve this. You probably already know what the answer is. Let me just go ahead and do it for you. Lambda is equal to, or lambda squared is equal to -4. So lambda is plus or minus 2i. All right, so what happens here? Plus or minus 2i. Well, what's going to happen is that you're going to end up with, well, you could probably take a guess, but it's very much like your second order differential equations. You end up with sines and cosines for this thing. And not only that, but you only have to solve for one eigenvector. And so we'll see why in just a sec. Let's go ahead and do that. So what is this? Yeah, let's go ahead and do it. So we have -2i and 2, and then -2 and -2i. All right, that's good. V1, V2. Oops. Because of the nature of complex numbers, if you find one eigenvector, then the other one is going to be a complex conjugate of it. So it ends up working out nicely. But let's see if we can work this one out. So if you multiply through, you get -2i times v1 plus 2v2 is equal to 0. On the bottom, I get -2v1 minus 2iv2 is 0. So at first glance, those don't look like the same equation, but they are the same equation. And if you don't believe me, what you could do is you could take one of those, take the top one, let's say, multiply the whole thing by -i. And when you multiply this by -i, you end up with a triple negative, and this becomes -2. When you multiply this by -i, it becomes -2i. Almost done now. Let's see. So pick one of them. I don't care which one. Let's do this one. And you get v1 is equal to -i times v2. So just solve one of those. They're both going to come up. You'll have similar solutions. They may not look identical, but it'll be similar enough. Now that we've got that, you can pick a number for v1 or v2. So let's choose v2 is equal to I, which I realize is an imaginary number, but if we do that, then V1 is going to be negative I times I, which is negative I squared. And just remember that I squared is negative 1. So V1 is positive 1. So this vector looks like this. Oh, yeah, that's right. So it turns out that the other eigenvector is the complex conjugate of this. Complex conjugate just means take all the i's, turn them into negatives. But we don't need both of the eigenvectors because of what this is going to look like. So let me write this down. So y, just write it like this for now. We'll deal with the constants in a sec. So you have eigenvector times e to the, what is this? E to the 2i t. So here's the cool thing about this is that you can take this and rewrite it using complex variables, using Euler's formula. And so here's how this is going to look. So this will be cosine of 2t plus I times sine of 2t. So this is because e to the ix is equal to cosine of x plus I sine of x. Just this Euler's formula from maybe Calc 2 or some other time. We did use it. I think I mentioned it, and then we discarded it pretty quickly back when we were doing the second order differential equations. It's the reason why you end up with cosines and sines when you do your stuff with the i's. Okay, so we're almost there. So the last bit is to, how does this work out? We're going to do, let's see, we have 1 and I, let's see, times, here, I'm going to write this just a sec. So cosine of 2t plus I sine of 2t, there's that, and then I times cosine of 2t, and then this is going to actually be minus sine of 2t. There we go. So all I did there is I took this and multiplied this stuff times 1 to get this, multiplied this times I to get this. And then the cool thing about this, without doing all that nasty algebra, is that you can separate this into the real part and the imaginary part. So here's how this will look, is the real part is this stuff, cosine of 2t, sine of 2t, there's a negative down there. And then the imaginary part is sine of 2t, cosine of 2t. And then these are going to be sort of the building blocks for your solution. Now the actual solution, so this is just sort of the work that I did. The actual solution is just constant 1 times this vector, negative sine of 2t. Whoops. There we go. And then C2 times sine of 2t and cosine of 2t. So you're going to gather all of the complex or all the imaginary stuff together. We'll practice this again on Friday because we kind of did this rushed at the end. So I'll get a better example that's a little bit more difficult. This one was actually too simple, and it kind of makes it look like it's way too easier than it is. So what your job is for Monday is you've got a whole bunch of these sort of systems. I think there's 11 of them. For Friday, though, you should try to go through and do the first half up until you get to the complex variables. When you get to anything that is imaginary complex variables, just stop, and we'll do that for Monday. But anything else you should be able to do for Friday. Do the best you can. You can also watch those videos from a couple years back, 5 years ago. If you get stuck, that's another place to go. Let me stop the recording if you want to come chat.